Hello everybody and welcome to our video on the substitution rule. So we're going to talk about a somewhat different situation for integrals than what we've dealt with so far. So let's take a look at this integral as an example. The integral of cosine of sine of x times cosine of x dx. So here we have a composition of functions, right? We have one function inside the input of another function. So we don't have any way to deal with this so far. Since we don't know any antiderivatives for this function, we'll need another approach. And so what we're going to do is make a convenient substitution and express this integral in terms of a new variable. So what I mean is, I'm going to pretend that this is a variable u. So here, I'm writing u equals sine of x. But in order to integrate, I need to have just one variable in my expression. So that means I have to figure out how to rewrite these other expressions in terms of u as well. So I'm going to do that by taking a derivative here. And I get that the derivative of u with respect to x is cosine of x. And what I really want is cosine of x dx, but if I multiply this dx across, I get du equals cosine of x dx. So what does that tell me? That tells me that I can take this whole integral and rewrite it as the integral of cosine of u times du. And that we do know an antiderivative for. The antiderivative for cosine is sine. So this becomes sine of u plus a constant. But since we were trying to integrate with respect to the variable x, we just substitute back our expression for u, which was sine of x, and we get sine of x plus c. Now, if you want to convince yourself that this worked for this problem, you could do so by taking the derivative of this expression and seeing that you get what's inside your integral after you do that. Okay, so let's actually take a look at a justification for this approach and the statement. So the statement of the substitution rule: if u equals g of x is a differentiable function whose range is an interval I and f is continuous on I, then the integral of f of g of x times g prime of x dx equals the integral of f of u du. So if you can get this expression in this form, you can substitute this in place. So, okay, well, how do we justify this? Well, the substitution rule is really just the integration equivalent of the chain rule, right? This is just reversing the chain rule. So let's start by writing out a derivative expression here. Cap f prime equals little f. Let cap f prime equals little f. So then if I take the derivative of both sides here, well, let me rephrase that. Since cap f prime is little f, if I take the derivative of cap f of g of x, I have to apply the chain rule. And so I get cap f prime of g of x times g prime of x, the derivative of the inner function, by the chain rule. So now we have an equation that relates these two expressions, and we're going to integrate both sides of that equation with respect to x. So I integrate cap f prime of g of x times g prime of x dx, and the derivative of cap f of g of x dx. So the definition of an antiderivative says that when you integrate a derivative, you get back the function, right? When you integrate a derivative, you get back the function. So in other words, so we get that the integral of cap f of g of x derivatives with respect to x is cap f of g of x plus c. Now, since we have defined u to be equal to g of x, that means cap f of g of x plus c is the same thing as cap f of u plus c. And then, by definition again, cap f of u plus c is the integral of the derivative of cap f. So finally, we've got this expression equals cap f of u plus c, which is equal to this, which is equal to our expression all the way back here. So in conclusion, the integral of cap f prime of g of x times g prime of x dx is equal to the integral of the derivative with respect to u of cap f of u du. But remember, cap f prime is the same thing as little f, so that gives us our final expression. Okay, so let's go ahead and just apply this to some more problems. Now the trick here is to remember that we're dealing with composite functions, right? You're dealing with expressions like f of g of x times blah blah blah, and this g of x inside is what needs to be u. So you're looking for a function inside of another function to make your substitution for. So when I take a look at this integral here, I see that I have 5x plus 7 inside my square root, and that looks like the only possible choice. So keep in mind, for some problems, there may be different expressions that could be picked for you, though maybe only one of them works well. So you might have to actually figure out what to pick for you. It might not be completely obvious immediately. But the first thing to think about is you're looking for a function inside of another function. So that's what we've got here. So I'm going to let u equal 5x plus 7. So then du dx, the derivative, is 5 dx. Sorry, du dx is 5. I skipped a step there. And then if I multiply dx across, I get du equals 5 dx. But I want to replace dx in my expression, so I divide the 5 across and I get du over 5 equals dx. So the key thing here is that when you make your substitution, you can only have one variable inside your expression. Once you substitute x out, you need to substitute everything out so that all of your expressions are now in terms of one variable, in this case, u. So when I do that, I get the square root of u times, and I replace dx with du over 5. Now I just need to rewrite this a little bit to make it easier to integrate. I'm going to pull the 1/5 in front and make the square root of u to the 1/2 du. And now we can take this antiderivative using the power rule. We add 1 to our power, that gives us u to the 3/2, divided by 3/2, plus c. Now remember, dividing by 3/2 is the same thing as multiplying by 2/3. So I can rewrite this as 2 over 5 times 3, which is 15, times u to the 3/2, plus c. And finally, whenever we're finding these antiderivatives in terms of x, you're going to be expected to write your answer back in terms of x. So we just have to redo that substitution. So replace u with 5x plus 7. Don't forget this power to the 3/2 power, plus c. Next. Okay, so here we look at example 3, and I see there's cosine of the square root of x. And so this looks like an interior function to me, right? Square root of x is inside cosine. So I think that's going to be my substitution. So we're going to let u be equal to the square root of x. And just to make the derivative easier, I'm going to rewrite that as x to the 1/2. So du dx equals 1/2 x to the negative 1/2 power. You may be hearing my 3-year-old playing drums in the background, so please try to tune that out if it's distracting. I'm sure they will be done momentarily. Okay, so we've applied our power rule, And we're going to multiply dx across. And what do we get? We get du equals. Now I'm also going to rewrite this 1 over 2 x to the 1/2 power, or the square root of x, times dx. Now, what I'm trying to replace in the function is this whole expression dx over the square root of x, which I have here. So I want to get rid of that 2. So I multiply that 2 across. I get 2 du equals dx over the square root of x. And that's good enough. So this becomes the integral of cosine of u times dx over the square root of x is 2 du. And so I can pull that 2 out in front, and I get 2 times the integral of cosine of u du. And the antiderivative of cosine is sine of u plus c, but don't forget to switch back to your variable x. So this becomes 2 times sine of the square root of x plus c. Okay, so one little aside I just want to mention here. Notice that whenever we take this derivative, we are always going to have to multiply the dx across in order to isolate that dx so that I can substitute it back in to the integral. We've done that on all of these examples so far, right? You're going to multiply that dx across. You're going to multiply that dx across, right? And every time. So from here on out, I'm just going to start my first step with my derivative. I'm going to jump straight to writing that dx across just to save one little step. It's not a lot, but you know, it saves a little bit extra time. So now I've got evaluate the integral of tangent of x dx. Now this one might not look like a composite function. But if we rewrite tangent of x as the integral of sine of x divided by cosine of x dx, now I have this expression cosine of x inside the denominator of our integral. So now we can rewrite this as a u substitution. So we're going to let u be equal to cosine of x. Then du is going to be negative sine of x, right? The derivative for cosine is negative sine, times dx. But what I really need is sine of x dx. Let me change that color. Sine of x dx. So I'm going to multiply that negative 1 across and get negative du equals sine of x dx. Now I've got the exact substitution that I want to make. So this becomes the integral of negative du over u, which is negative the integral of du over u. That's negative the natural log of the absolute value of u plus c. Now remember, of course, that you always need to substitute u back in. Just cosine of x. Now, this is totally fine. This is a perfectly valid answer to the question, but it's not the way that the integral of tangent of x's result will usually be written when you look at it. What you will usually see is they will apply the log property, right? Because this means negative 1 times ln, the absolute value of cosine of x. So they'll use the log property to move that negative 1 into the power position in here. And then since that's cosine of x's absolute value to the negative 1 power, they rewrite this as the natural log of 1 over the absolute value of cosine of x plus c. And then 1 over cosine of x is secant of x. So this is ln of the absolute value of secant of x plus c. So this is the usual form that you will see. Okay, let's move along. Yeah, we're doing a whole bunch of examples of these. There are really an untold amount of substitutions that you can do. And it would be honestly completely impossible for me to cover every circumstance that comes up where U substitution is appropriate. So I'm just trying to do a lot of examples to give you a good idea of how to apply the principles here. But you really do have to be creative sometimes in coming up with ways to apply U substitution. So in this case, though, I'm going to take a look. And again, I'm always looking for an inner function, looking for a function inside another function. And here, we've got z squared plus 1 inside the square root. So that's what I'm going to try. Let u equal z squared plus 1. Then du is going to be 2z dz. But what I need to replace here is not 2z dz, it's z dz. So I'm going to divide that 2 across, and I get du over 2 equals z dz. And now I've got everything I need to make my substitution. So this becomes the integral of, well, you got the square root of u, and z dz is going to be replaced with du over 2. So now we'll just rewrite that. I'll pull the 1/2 in front and write the square root of u as u to the 1/2 du. And now we can take our antiderivative. That's 1/2 u to the 3/2 power divided by 3/2 plus c. Now in this case, we get kind of lucky. Our denominator, 2 times 3/2, the 2's are going to cancel. So that makes that a little easier to deal with. So this is just 1/3 u to the 3/2 plus c. And finally, I'll substitute u back in. This is 1/3 z squared plus 1 to the 3/2 plus c. Moving on. Again, look for a function inside of another function. Here I've got 2x squared plus 3 to the 7th power. Now, you might be tempted to try to multiply this all out, but if you try to multiply this binomial, 2x squared plus 3 to the 7th power, that's going to be tough, right? That's a very long multiplication. It's going to take you a really long time. It's technically possible, and if you entered this into a computer algebra system, that's usually how it would evaluate the derivative, but that's very, very cumbersome and inefficient. We can just make a substitution and say let u equal 2x squared plus 3. Then du will be 4x dx. But this becomes tricky because I don't have an x dx here. So what I'm going to do is first rewrite my integral, still in terms of x, because I noticed that x cubed can be written as x squared times x, and so I can pull off a factor of x here. So I'm going to take this x cubed and write the x squared up front. I'll still have 2x squared plus 3 to the 7th, and then I've got x dx here. So notice all I did was took that x cubed and split it into x squared times x. But for convenience, I wrote them in different parts of the integral. So now when I look back at du, I have du equals 4x dx, so du over 4 equals x dx. So that's pretty good, but I still have a problem because what do I do with this x squared? So I'm just going to put a parentheses there for now. 2x squared plus 3 to the 7th, that's just u to the 7th. And x dx is du over 4. So we got to figure out what to write in here in terms of u. How do I write x squared in terms of u? Well, I look back at the stuff I have with u, and I notice, oh, in my original expression, I have an x squared. So if I just solve that expression for x squared, I get u minus 3 over 2 equals x squared. Oh, problem solved. Okay, so now let's go ahead and simplify this a little bit. we've got a denominator of 2 and a denominator of 4. 2 times 4 is 8, and I'll pull that 1/8 out in front of the integral. And then inside, we've got u minus 3 times u to the 7th du left. Now, I'm not done. I still can't integrate this. I can't do anything with products of two different functions inside of an integral. There's no equivalent product rule like we have for derivatives, right? So what do we do here? Well, we distribute this. And then this becomes 1/8. The integral of u to the 8th minus 3u to the 7th du. And now we've got something pretty manageable, right? 1/8 times u to the 9th divided by 9 minus 3 times u to the 8th divided by 8 plus c. Now I can distribute this and replace my u at the same time. So 1/8 times 1/9, that's going to be over 72. And u to the 9th will become 2x squared plus 3 to the 9th power. Minus 3 over 64 times 2x squared plus 3 to the 8th power. And still need that plus c. Okay, that's it for that example. Moving on. So now we got to talk about the substitution rule for definite integrals. So if g prime is continuous on the interval from a to b, and f is continuous on the range, the outputs that you get for g, then the integral from a to b of f of g of x times g prime of x dx equals the integral from u of a to u of b of f of u du. In other words, what we're saying here is that when you make a u substitution to evaluate a definite integral, you must convert your bounds of your integral to the bounds for your new variable u. So let's take a look. We're going to look at an example here, which I've already typed up just because we're going to be looking at some pictures to try to make sense of it. So let's take a look here. We've got the integral from 0 to pi halves of sine of 2x dx. So we're making a very simple substitution here, right? This is u equals 2x, so du equals 2 dx. So divide the 2, you get du over 2 is dx. And now we're evaluating u at my original bounds. So I plug in 0 into u. 2 times 0 is 0. And then I'm evaluating u at pi over 2. So I plug in pi over 2. 2 times pi over 2 is just pi. Therefore, the integral from 0 to pi over 2 of sine of 2x dx is now going to be the integral from 0 to pi. Those are my new bounds for the new variable. And I've replaced u inside sine, 2x with u. And dx gets replaced with du divided by 2. So now when I integrate, this becomes 1/2 negative cosine of u, evaluated from 0 to pi. I move that negative out in front, so that's negative 1/2 cosine of pi minus cosine of 0. Cosine of pi is negative 1. Cosine of 0 is 1. Negative 1 minus 1 is negative 2. Negative 1/2 times negative 2 is 1. So, all that is to say, the area under the curve from 0 to pi over 2 of sine of 2x dx is 1. Now let's take a look at the graph of these two functions. So this is the graph of y equals sine of 2x from 0 to pi over 2, right? This is pi over 2 right here. So the area under this curve is equal to 1 square unit. Now when we make our substitution to make this thing integrable, our graph changes. We now have the graph of 1/2 sine of u. So two things changed with this graph. First, the height of the function changed, right? That 1/2, it's actually, technically we are compensating the width of the rectangles in our definition of our integral, right? But when we write this expression out, what we end up looking at is the function 1/2 sine of u. So what has to happen here? So our bounds have to change because now we have a function that is 1/2 the height of our previous function. So in order to get the same area under the curve that we had before, what have we had to do? We've had to stretch out our bounds so that now we're integrating not from 0 to pi over 2, but after the substitution, we're integrating from 0 to pi. And once we do that, we'll still get the same area because we've compensated for the change in the function by stretching the bounds that we're integrating over. Okay, so hopefully that makes sense and gives you some understanding of why it is absolutely critical that you always change your bounds when taking this approach to evaluating these definite integrals. But let's go ahead and tackle some problems. Now, there is one alternative that you can use. So we're going to take this first problem on in two different ways. So the first thing I'm going to do is exactly what I just did. I'm going to just make the substitution as part of the definite integral, work through it like normal, etc. And then I'll show a slightly different approach. So we've got the integral from e to e to the 4th dx over x times the square root of ln of x cubed. And when I look at this, it's a little hard to tell what to pick because my first thought might be I have the square root of ln of x cubed. So I've got that square root of ln of x all inside this cubed function. So that might be my first thought in terms of how to pick u. But if I do that, when I try to take its derivative, I'm going to get something really messy. And what I notice is if I instead pick ln of x, the derivative for ln of x is 1 over x, which I have right here in my expression. So that makes me think that if I pick ln of x, that's going to be easier because du will be 1 over x dx. Okay, so we go to make this substitution, and we get 1 over x dx is du. And then all we've got left is the square root of u to the 3rd power. But we have to change our bounds. That's the key here. So ln of e is just 1, and ln of e to the 4th is just 4. So my bounds become 1 and 4. And now I'll rewrite this integral a bit further. This is the integral from 1 to 4. The square root of u is u to the 1/2 to the 3rd power. This is du over u to the 3/2 power. And I'll rewrite that one more step. That becomes u to the negative 3/2 du. And now I can take my antiderivative. So I add 1 to my power. That becomes u to the negative 1/2 divided by that new power, negative 1/2. I want to evaluate this from 1 to 4. Before I do that, I'm going to rewrite it a little bit further. Instead of dividing by negative 1/2, I'll write this as multiplied by negative 2. And instead of u to the negative 1/2 power, I'll write this as 1 over the square root of u. And then I'm going to evaluate that from 1 to 4. It's a little buggy there. Let's try that again. Evaluate that from 1 to 4. That's going to be 1 over the square root of 4 minus 1 over the square root of 1. That's negative 2 times 1/2 minus 1. And what does that give us? That's going to give us -1 plus 2. For some reason, I think I made an arithmetic mistake. I should probably check for that. Let me make sure. No, I think everything's good. I think I don't think I made any silly mistakes there. Just for some reason, those numbers didn't look right. Yeah, that's fine. Okay, great. Sorry for the delay. Moving on. I wanted to be extra careful with that because we're about to do this problem again in a slightly different way, and would have been real confusing if we'd gotten different numbers there. So let's go ahead and tackle this a slightly different way. So this time, I'm going to do just the antiderivative first, because what the fundamental theorem of calculus tells us is that once we know the antiderivative, we can just plug in the endpoints into that antiderivative. So now I'm not going to deal with the bounds at all. I'm going to evaluate my antiderivative and switch all the way back to the variable x before I evaluate the definite integral. So I make the same substitution, so I'm not going to re-explain all that. I get du over the square root of u cubed. And that's going to give me the integral of u to the -3/2 du. And when we take our antiderivative, we're going to get the same thing. So again, I'm going to skip a little bit there. I'm going to get -2 times 1 over the square root of u plus c. But this time, I'm going to substitute back to my original variable, u equals ln of x. So I get -2 times 1 over the square root of ln of x plus c. So now that I know the antiderivative for this function, when I go to evaluate my definite integral, I've already done all of that part. And since I've switched back to my original variable, I can use my original variable's bounds. So here we get -2 times 1 over the square root of ln of x, evaluated from e to the evaluated from e to e to the 4th power. That was a little bit of a tongue twister. -2 times 1 over the square root of ln of e to the 4th minus 1 over the square root of ln of e. This becomes -2 times 1 over the square root of 4 minus 1 over the square root of 1. That's -2 times 1/2 minus 1. That's -2 times -1/2, which is 1. Of course, it's the same thing. So here's the key differences. In this approach, instead of manipulating the definite integral the whole time, I just went to finding the antiderivative of the function, and I finished that and rewrote it completely in terms of x first. Then I just applied the fundamental theorem of calculus directly, wrote my antiderivative, evaluated it at the endpoints. And since our antiderivative is in terms of our original variable, I can use the original bounds that we started with. In the other version here, we wrote everything as a definite integral, so when we change variables, we have to also change bounds, or these things won't be equal anymore. And what doing it the approach on the left allowed was we didn't have to switch back to the variable x. We could immediately evaluate this thing instead of switching back to x. Either method is fine. The method on the left is usually a little bit faster, usually, but there are cases where it's not, and cases where I will prefer the approach on the right. So the approach on the left saves a couple steps on average, but sometimes when it's hard to evaluate the function at the endpoints, that kind of situation, or when there's just a weird manipulation that I need to do in an integral, I might take the approach on the right instead. But usually the approach on the left, just a slight bit faster. Okay, so let's move on to another example. Now this is another example where when we try to evaluate this integral, we might make a mistake on what we pick for u. So I'm going to make that mistake just so that you can see what happens. So initially, you know, you may not even want to write this down, who knows, but I do want you to think about what I'm doing here. I see this in the denominator, and that makes me think, oh, I can use that as my u. U equals 1 plus sine squared of x. But if I do that, I get du equals, the derivative of 1 is nothing, and for sine squared of x, it's 2 sine of x times cosine of x. I have to apply the chain rule there. And the problem is I don't have anything like this in my integral. I have cosine of x dx, but I don't have a sine of x. And I don't have any way to rewrite it to get one. So that's done. Oh no, that did not work. I made a mistake. And that's okay. That's going to be pretty frequent. You know, you're gonna be working on a problem and you're just gonna try a substitution and it's not gonna work, and that's okay. So you try a different substitution. So here what I'm gonna do is first rewrite this so that it's easier to see what the correct substitution is. So I'm just rewriting sine squared of x as parentheses sine of x squared, because then it becomes more obvious that this is where our substitution should be. So now we can pick the correct substitution. Let u equal sine of x. Then du is cosine of x dx. Why did I put dx twice there? I already had dx. Cosine of x dx. And now this substitution is pretty straightforward. This becomes the integral of du over 1 plus u squared. But I need to evaluate my bounds. So when I evaluate u at 0, that's sine of 0, which is 0. And when I evaluate u at pi over 2, that's sine of pi over 2, which is 1. So my new bounds should be 0 and 1. And this becomes tangent. The antiderivative of 1 over 1 plus u squared is tangent inverse of u, evaluated from 0 to 1. So this gives us tangent inverse of 1 minus tangent inverse of 0. And we know that tangent is equal to 1 when our angle is pi over 2. So tangent of pi over 2 is 1, which means pi over 4. Tangent of pi over 4 is 1, so tangent inverse of 1 is pi over 4. And likewise, tangent of 0 is 0, so tangent inverse of 0 is 0. So final answer is pi over 4. Okay, so now let's do an application problem involving u substitution. So a water tank ruptures at a rate of R of t equals 200 times e to the negative 1 over 25 t liters per minute. How much water leaks out during the first 2 hours? Well, the first thing is our function is in terms of per minute, so we want to convert our time to minutes. So 2 hours is 120 minutes. Keep an eye out for that stuff in some of your homework problems. It's easy to get tripped up on that. So when I talk about a rate, well, what I'm asking here, how much water leaks out, is the net change in the water over time. And we know that the integral of a rate of change is net change. So this is a rate of change. The integral of a rate of change is net change. So that means that the amount of water that's leaked out is the integral from 0 to 120 minutes of this function 200 times e to the negative 1 over 25 t dt. So I think the substitution for this problem is pretty obvious. We need to replace what's inside the exponential function. So we're going to let u be negative t over 25. So that means du will be negative 1 over 25 dt. And when we evaluate u at 0, I'm just going to get 0. And when I evaluate u at 120, I'm going to get negative 120 over 25. And those are both divisible by 5, so that's going to simplify to negative 24 4th over 5. So now our integral becomes the integral from 0 to negative 24 over 5 of 200 times e to the u times, and I should have rewritten dt here. So let me just move that a little bit. Multiply the 25 across, and multiply by negative 1 as well. This gives us negative 25 du equals dt. So let's replace dt with negative 25 du. Okay. Now we've got 200 times negative 25. So 200 times 5 is 1,000. So that's going to be 5,000. So negative 5,000. And I'm going to pull that constant in front of the integral. And all that's left inside is e to the u du. So this becomes negative 5,000 times e to the u evaluated from 0 to negative 24 over 5. That's negative 5,000 times e to the negative 24 fifths minus e to the 0. And now we're just going to rewrite this a little bit more. This becomes 1 over e to the 24 fifths. And e to the 0 is 1. And one more step here to rearrange this. Multiply the negative 5,000 across, but I'm going to change the order. Negative 5,000 times negative 1 is a positive 5,000. And negative 5,000 times this is just negative 5,000 over e to the 24 fifths. Now that's the exact answer. I'm fine with leaving the answer like that. If you want, you can plug it into a calculator to get a decimal, but that answer is perfectly good. Okay, so let's move on to a related topic, which is integrals of symmetric functions. So oftentimes when computing integrals, you can make your life a whole lot easier if you notice that you have a symmetric function, a function that's either even or odd. And we want to just kind of keep an eye out for that. So we're going to take a look at this idea real quick. Suppose that f is continuous on the bound from negative a to a. If f is an even function, that is f of negative x equals f of x, then the integral from negative a to a of f of x dx is twice the integral from 0 to a of f of x dx. Now, the visual justification for this is very simple. You look here at your picture. If it's an even function, f of negative x equals f of x, that means you get a mirror image over the y-axis. And so the area from 0 to a is going to be the same area from negative a to 0. It just looks mirrored. So instead of integrating from negative a to a, you can just double your integral from 0 to a. So sometimes you may see that in problems, and it can just cut down the work a little bit. It's not a huge time saver, but sometimes it makes the computation a little easier. Now, what can be a really huge time saver is if you notice that a function is odd, that is f of negative x equals negative f of x, then the integral from negative a to a of f of x dx is 0. Right? So if we look at this picture again, the visual justification is very simple. You've got an odd function, so it's a reflection 180 degrees around the origin. So whatever you get left of the y-axis will be the mirror image but flipped over from the what's right of the y-axis. So in this case, we've drawn this function where the positive side is on the left. So you get a positive area here. And then this part of the integral will be negative. I mean, the area itself is positive, but remember, the integral treats areas under the y-axis or the x-axis as having negative value. So this portion is going to be the negative of this. So those are going to cancel out when you take your integral. So we're going to actually look at the proof for part B, but I think this visual justification should make it pretty clear. So first, we're going to split the integral into two pieces at 0. So we'll write our integral from negative a to a of f of x dx as the integral from negative a to 0 of f of x dx plus the integral from 0 to a of f of x dx. And then we're going to make a u substitution. So we substitute u equals negative x on the integral over the interval from negative a to 0. So when we do that, so this is the integral we're making the substitution on, we get du equals negative dx, right? The derivative of u is negative 1 dx. Or I should say du. The derivative of u with respect to x is negative 1, so du equals negative 1 dx. If we multiply the negative 1 across, we get that negative u is also equal to x, so I can substitute x in place of negative u. And when I evaluate my bound u of negative a, I get a. And when I evaluate u at 0, I get 0. So, in other words, here is our left-hand side, this negative a to 0 integral. We're just doing the negative a to 0 part here. I make the substitution. X becomes negative u. Dx becomes negative du. My bounds change to a to 0. Now, this next equality is nothing crazy. I just took the negative that I had here and moved it in front of the integral. And now here, I'm looking at the bound, or the function f of u, but remember, we're assuming that f is odd. We're proving part b here. So f of negative u equals negative f of u. So when I take this negative inside this function and I, so to speak, pull it out in front of the function, it's going to cancel the negative that's already there. And that's why we end up with a strictly positive expression here. Now this is a property discussed in the areas and definite integral video, which is that when you flip the bounds of an integral, it gives you the negative integral. I think I might have actually flipped these around. Okay, so I said the third here, that should say fourth, and then this should say third. I don't know why I wrote those in the wrong order. So the third equality comes from the symmetry. The fourth one comes from property 6 in the areas and definite integral video. And the last one, the negative integral from 0 to a of f of u du equals negative the integral from 0 to a of f of x dx. All we're doing is changing the variable there, and the fundamental theorem of calculus doesn't care what the variable name is when you evaluate the integral. So that doesn't change anything. Okay, so let's apply this idea here. Let's go and take a look at an integral. Oh, I guess I should have gotten to the last part. Here, we found that the integral, this first part of the integral is equal to negative the integral from 0 to a. So when we plug that into our original expression, we replace this with this. Then you see these are just going to cancel each other and give us 0. Okay, so a little reminder from the way back. Cosine of x, secant of x, and all polynomials that only have even-powered terms, like 3x to the 4th, x squared, etc. Those are even functions. Sine of x, cosecant of x, tangent of x, cotangent of x, and any polynomials with only odd-powered terms are odd functions. Now, it becomes a little more complicated when you're dealing with combinations of those functions, and so we'll usually have to actually check. So here, evaluate this integral. Negative pi over 4 to pi over 4, sine of x plus x to the 7th cosine of x dx. When I see something like this, in particular because it's negative a to a, we have the same value on the integral bounds, but one of them is negative. That should tell me to pause for a second and see if I can use symmetry to help me. So let's check the symmetry. If we're thinking about the function sine of x plus x to the 7th cosine of x, what happens at negative x? So I get sine of negative x plus negative x to the 7th cosine of negative x. And sine is an odd function, so sine of negative x is negative sine of x. And negative x to the 7th is an odd function, so negative x to the 7th is also negative 1 times x to the 7th. But cosine of x is even, so cosine of negative x is the same thing as just cosine of x. And finally, I have a negative in front of both of these terms, so I can factor that out and make it negative 1 times, parentheses, sine of x plus x to the 7th cosine of x. But that's the same thing as the negative of my original function, negative 1 times f of x. So in other words, f is odd, and so when I look at this integral from negative a to a of f, I don't have to do any computation. The answer is 0. But I do need to justify it by showing that the function is an odd function. The truth is, you would not really be able to integrate this function, at least not with the tools you have currently. Technically, this would be integrable with some other tools, but using this property allows us to bypass that. Okay, now we're going to take a look at one last example applying the substitution rule. If f is continuous on the real numbers, prove that the integral from a to b of f of x plus c dx equals the integral from a plus c to b plus c of f of x dx. If you're asked to prove something like this, and you see you've got an inner function x plus c here, odds are you should just try making a substitution. Don't worry too much about coming up with some tricky approach. You know the substitution rule, try to use it. So we're going to let u be equal to x plus c. Then du is just dx. That's a real nice substitution. But u evaluated at a is a plus c, and u evaluated at b is b plus c. So that implies, by the substitution rule, that the integral from a to b of f of x plus c dx is the integral from a plus c to b plus c of f of u du. And this is, of course, just equal to the same integral in terms of x. Again, that's a fundamental theorem of calculus thing, right? The fundamental theorem of calculus says that when you evaluate the definite integrals, you take the endpoints and you plug them into the antiderivative. It doesn't actually, evaluating them isn't related to what the name of the variable is. Okay, well that's it. That's everything on the substitution rule. Thank you for watching.